can't say good morning because at the moment I'm in Finland, so it's still morning for me, but I realize it's afternoon for the Singapore friends. Good afternoon and morning to everybody. So welcome to today's symposium. You are currently in Team 2, Robotics and Sensors. Together with Julian from University of Glasgow, myself, Pei Ling from SIT, we will be moderating the session for this theme. So without further ado, may I introduce the second speaker in this track, Dr. Henrik Gollee from University of Glasgow. So Henrik is a senior lecturer with the James Watt School of Engineering, University of Glasgow. His research interests are in the use of control engineering methods to understand how humans control their movements, how they learn, and how they adapt to changing conditions. He is particularly interested in using this understanding to develop assistive and rehabilitation methods for people with neurological impairments. His presentation topic today is Data-Driven Intermittent Control for Adaptation and Learning in Human Movement Control. Over to you, Henrik.
Thank you for your kind introduction and for the opportunity to present my work at this symposium. My presentation today I'm going to sort of present a bit of a more enabling technology I've been working on for a number of years. And this is really motivated by the question, how can we optimize rehabilitation interventions? And to do this, I think what we need to develop is understanding how humans actually control movement and how this changes in neurological dysfunction and neurological disorders, and how we can use then our understanding of control to optimize our interventions in rehabilitation. And that includes things like how can we optimize robotic interventions, how can we optimize physiotherapy interventions. Now, motor learning as such is a set of processes which lead to permanent change in the capability for responding. But if we learn a movement, we don't just learn a specific movement, we learn something which is more generic than that. So if we look at somebody walking, we can walk at different cadences, we can walk with different speeds and so on. But that's in principle quite well understood, but there are a number of open questions which are still not really explained and not really understood very well. For example, movement is variable. How do we, what's the role of variability there? And movement is, develops over time. How do we actually learn that? What are the components of that? What facilitates that? Now, in computational motor control, we basically try to understand the overall control principle of human movement. We don't look at necessarily at specific aspects of brain functions or things like that, but try to understand the overall concept. And questions which arise there is, for example, what is the source of variability in movement, and which paradigms facilitate learning and adaptation and relearning? How can this translate to neuromuscular rehabilitation? The question arises, what is the role of variability in movement? Is it important? It is well known that a lack of variability is actually a sign of pathology, and we can maybe use diagnostics of variability in diagnostics of movement disorder. And what approaches can then facilitate relearning or rehabilitation of patients, for example, with stroke or with spinal cord injury? I'm going to take a long step back to the 1940s to start with. And this is work originally developed by Kenneth Craig, who was the first director of the Medical Research Council in the 1940s. And he worked on how humans actually track, in this case, enemy aircraft. And these results were later repeated. So what you find is that even if the target changes continuously, there are some properties of the human response, of the human motor response, which are quite characteristic. One is that it's variable, so it's not constant. You have discontinuities, you have response limitations. So you have these small changes here, which happened at various periods of time. You have frequency constancy, so the frequency of change is fairly constant. And you have something which is called the psychological refractory period, where you basically you react to a change in target, and even though the target has changed again, you first have to execute the movement which you have started before you can actually correct that. Now, all of these things are well known in physiology, but it's not understood what is the principle underlying that. So they have been observed, but they haven't been included in a model which can explain that. So we don't really understand what is a source for that. So as was mentioned in the introduction, I'm a control engineer, and I've been looking at feedback mechanism which can model human movement control. The most basic model for feedback control is just continuous feedback. So you measure a joint angle and you apply a certain control signal to based on that. The serial ballistic theory, introduced by Kenneth Craig initially in the 1940s, basically is based on the idea that you observe continuously, but you only act intermittently. In other words, you have a open loop trajectory which your limb follows, and you correct this based on intermittent feedback, based on some event trigger. How could this be implemented in terms of control engineering? But getting a little bit technical here. So you can have a standard observer predictor feedback or state feedback control loop. That's a continuous control loop up here. And you just add a couple of blocks here. One is a trigger block, which decides when this feedback is used. And the other is a hold block, which generates this open loop trajectory. That gives you an additional parameter basically to play with, and that's the threshold trigger. And I want to just briefly show you what this looks like. The yellow line here is a continuous control signal. That's a control input, that's a control output. The more reddish line is the intermittent controller, and the dots indicate when feedback is used. So you use feedback much less often, not continuously, obviously, and you do intermittent correction, make intermittent corrections here. And interestingly, the output looks pretty similar to the continuous controller. So that means, in other words, that just looking at the output, as we do with, for example, if we observe movement control, we can't really necessarily tell whether it's intermittent, the underlying controller is intermittent or continuous. Now, if we change just the threshold in this case, we get a control response which looks like the one below here in the lower graph, where the points where we use feedback are very rare, but we still control the system quite well. But of course, our disturbance response is much less. So we can sort of adjust how well we react to things. And this is something which we observe in human movement control, of course, as well. I've done a fair bit of work on trying to model movement with this paradigm. We have a computational framework for that. And so we try to apply this to various kinds of movements. One was a simple mouse movement where a pointing task was conducted. where the user was asked to basically move the mouse between these two areas, which have variable width and variable distance. So we ended up with 8 conditions in this case. And if you look at the recordings, they look fairly stereotypical, but if you actually look at them in more detail, you see there's quite a bit of variability. How can we explain this? You could just add noise to the system, or if you apply an intermittent control framework, then you can actually basically develop a model for each of these pointing tasks. And you have a range of models in this case. You optimize the model parameters individually and have a range of models which can then display in this way. But crucially, you can replicate the variability which we observe in the recordings of data. These are the blue lines here, and the red lines overlaid are our models, which replicate this without any additional noise in the system. So variability purely stems from having this intermittency. That's quite an important feature which we can replicate here. You can also replicate various aspects of variability here. Now, to move things forward, our initial implementation of these systems are based on state feedback control systems. So the whole is basically a state feedback system, purely deterministic. We have now introduced data-driven approaches into this. We are using Gaussian processes for the hold element of our control system. That allows us specifically to actually capture uncertainty and unpredictability of responses. So the way Gaussian processes work is they are as a modeling technique essentially, which allows us to model systems with very few data points. So as few as 20 to 100 points allow us to develop a stochastic model. The stochastic model includes a mean representation, but also basically a spread or a confidence limit. And over time, this confidence limit with uncertainty propagation will reflect the level of certainty we have in the solution. And we can apply this in the context of intermittent control by actually using this uncertainty propagation to see when we actually have to use feedback again. Okay, we have applied this successfully in the context of our intermittent control system. We were able to replicate our previous results, and using GPs, we were able to actually introduce additional sort of variability in the system, which make the model basically more like human movement control, or what you observe in human movement. Okay. I want to kind of summarize where this can actually be used, how this can be applied. What are therapeutic approaches related to intermittent control in this context? We have on a sort of theoretical level or high level level, we can use intermittent control to have online response selection. We can have repetition without repetition. And I think that's key, one of the key aspects in rehabilitation, that we want to develop rehabilitation systems which don't necessarily just repeat the same movement, but which vary the movement, which vary the task, and therefore lead to what we observe in natural learning or relearning. So we introduce variability here. Having these open loop trajectories allows us to determine causal relationship within a closed loop setting, and that really facilitates system identification, which is key for adaptation and relearning. And therefore, we believe that we have shown that this opening of the loop is really a key aspect of the human being able to learn, and also technical systems then being able to identify what's going on. Now, applications of this range from, or what I'm working on currently includes ultrasound imaging of muscle, where we use not just EMG recordings to see what's actually going on with the muscle, but actual movement of the muscle from ultrasound recordings to see what is actually the input to the movement, what causes the movement. We were able to detect very small movements, for example, in spinal cord injury, which appear to be very relevant to neural recovery following paralysis. We have been using functional electrical stimulation of muscle in this context. We are combining this with robotic applications and with VR for human movement experiments. I have been working on abdominal FES, as Manuel mentioned earlier, to help people with breathing. We have combined it with ultrasound imaging of the muscle. And our main application area actually is, and which motivates all this work, is applications in spinal cord injury rehabilitation. Okay. Now, thank you very much for your attention here. I want to mention some of the collaborators, or acknowledge the collaborators, specifically the Queen Elizabeth National Spinal Injuries Unit, which really allows us to apply our work in settings with patients, primarily spinal cord injury patients. Thank you very much.
Thank you very much, Henrik. You have very kindly brought us through a very informative session on human motor control, starting from the theory to your research methodology and then to applications. So thank you very much for that detailed explanation. Now, moving on to our third speaker, we have Professor Vinod Prasad from SIT. Vinod is a professor with the Information Communication Technology cluster at SIT. His research interests include digital signal processing, brain-computer interface, and its applications in neurofeedback, neurorehabilitation, neuroprosthetics, and assistive technology devices. Today, his presentation topic is brain-computer interface-based neurorehabilitation. Over to you, Vinod.
Yeah, are you able to hear me? Am I audible?
Yes.
Okay, thank you. Thank you very much for your introduction. Good morning to the attendees from Glasgow, and good afternoon to my colleagues in SIT. So let me quickly take you through a short presentation about brain-computer or brain-machine interface-based neurorehabilitation. So I'm Vinod in ICT cluster in SIT. So this gives an introduction to BCI or BMI, brain-machine interface. Basically, every mental task has a unique neural signature. And using appropriate brain signal acquisition techniques, it is possible to decode these neural signature with a fair amount of accuracy. So that is a fundamental principle behind brain-machine interface. So a BMI translates brain activity into different command and control signals for controlling external devices depending upon what applications we want to use, be it for rehabilitation, developing prosthetic device, wheelchair control, speller device, serious computer games, or any other assistive technology devices. So here you see an overview of the brain-machine interface. Fundamentally, we need to acquire the brain signal, and then we have to do some signal processing, basically to remove the noise, to improve the signal to noise ratio, to extract the most relevant features corresponding to the mental task that we are trying to decode. And then finally, we go into the machine learning classification, and then interface with the output device. It can be any applications that we discussed earlier. And the last, but not the least important, is the feedback. So the BCI system should also give a feedback to the user, because it is with that feedback, the user try to do a self-regulation or a self-adjustment of the brain rhythms for performance enhancement, which is very important in BCI. So this is the overview of BCI. And BCI is a potential technology that aids in neuroplasticity, which means that the brain has a remarkable ability to rewire the damaged neural networks. And BCI-based rehabilitation enhances neuroplasticity. So let me go into some of the works that we have done in the past 1 decade or more, slightly in that period. We started our research with simple motor imagery classification. So classification of imagination of movement of left hand versus right hand, left leg versus right leg, and so on. So these are very simple motor imagery classification. Of course, many researchers have done a lot of work in that. But what we have done is addressing two important research problems. One is called an inter-subject variability, which means when a person is doing motor imagery, imagination of movement of a body part, the electroencephalogram or the EEG frequency bands that are discriminative to those motor imagery tasks vary from one person to another person. That is called inter-subject variability. And it is important to track and detect these discriminative frequency bands for every individual subject. And that is called the accurate and robust method to track inter-subject variability. So just to show in this diagram, what you see is the first two waveforms on the top row, the first row. You can see subject 1, the dark or the bold line indicates a reduction in EEG power. So when the person is actually imagining a movement. Now, let me explain to you that when we actually make a movement, even before the movement, there is a planning, there is a preparation, and then we execute the movement. So movement, the actual execution movement is preceded by a preparation phase, which is preceded by a planning phase. So even in the planning and preparation phase, we are able to detect the intention of movement. So during that intention of movement, you will see a reduction in power, as you can see by the bold line here, which is recorded in the C3 electrode. And if you can look at the topographic map here, C3 is located in the left hemisphere of the brain, because in this graph, the person is doing right hand motor imagery. So you know that when the person is doing right hand motor imagery, it is reflected in the motor cortex in the left hemisphere of the brain, which is picked up by the electrode C3. So this power reduction is the neural signature that we are looking for. If it occurs in the left hemisphere, it implies a movement imagination of the right hand and vice versa. Now what you see here, subject 1, the discriminative frequency band is 9 to 13 Hertz. Whereas when subject 2, the bottom left plot, performs the same task of right hand motor imagery, you can see the discriminative frequency band is different, 10 to 12 Hertz. So we came out with an adaptive method that tracked these discriminative frequency bands and classify motor imagery. That is the first work, which we achieved with about 82% classification accuracy. Now moving forward, the second problem that we addressed is intra-subject variability. So when the person is doing motor imagery brain-computer interface experiments, when the same person is imagining a task over a period of time, that means the experiment starts at time t is equal to 0. As time elapses, you can see that there is a change in the attention and many cognitive aspects of the patient. As a result, the discriminating EEG bands also shift over time. So it is important to keep track and adaptively detect the shift of frequency bands to enhance the classification accuracy and increase the robustness of the system. So the second problem that we addressed is detecting the intra-subject variability during motor imagery BCI, classification of left hand versus right hand, left leg versus right leg. We have an accuracy about 88%, which is the best reported in literature using non-invasive EEG BCI. Okay, now let me show you a simple game because we want to entertain the patient. So we did this interface with a simple game. It's called a ball sorting game. Let me play it.
Game is an EEG-based brain-computer interface game. Here the EEG signals are collected from the 64 EEG electrodes placed on the scalp of the subject. Let us see how this game works. In the game, subject has to sort the incoming ball to the basket with the same color by moving imagination. If the incoming ball is blue and the blue basket is on the left side of the screen, then the ball should be sorted to the left side. In order to sort the ball to the left side, subject has to imagine their left hand movement. The brain signal generated at the time of movement imagination will be collected by the EEG electrodes and it will be decoded to control the ball movement.
So I hope you got the gist of the story there, and this is a simple ball sorting game. Now moving forward, discrete classification like left hand versus right hand imagination is not sufficient enough for actual rehabilitation. So what we have extended further is that can we decode imagination of movement of hand, a chosen hand. Let's say we have a right hand paralyzed person. So we are trying to decode the imagination of direction of movement of his right hand in different directions. So the person is not actually executing the movement, he's only imagining. So in this diagram, what you can see, this is a clinical study that we have conducted in National Institute of Mental Health and Neurosciences, NIMHANS in Bangalore. Of course, I forgot to mention that I joined SIT about 5 months back. So in this experiment, what you can see that the stroke patient's right hand is completely paralyzed. The power is 0. And let me show you the experiment here. So what you can see here is at the start of the experiment, you have a hand which is at the neutral position, which will tell the patient that get ready. And after some time, you have a bug. That bug appears on the left side of the monitor or right side of the monitor randomly. It can be either left or right. Now, if the bug appears on the left side of the monitor, the patient will have to imagine he is moving his paralyzed arm to the left direction and tap onto the bug. And vice versa. If it is on the right hand side, he will have to do that. Now, this is the movement imagination period. Our system, BCI system, is trying to decode the imagined direction of movement. And the imagined direction, which is left, you can see it is interface in a closed loop fashion with the BCI system, the robotic arm, which is driven to the respective direction. So this is done in different directions. That is about motor imagery on stroke patients. We have seen using Fugal maze assessment method, there is an improvement in the plasticity there. Moving forward, another piece of work that we have done is traditionally when a patient is affected with stroke and admitted to a hospital, the first thing that they do is that take a scan, usually an fMRI or a CT, evaluate the cortical impairment. After the preliminary 2-3 days, in the intensive care unit, then the patient will be prescribed for rehabilitation therapy. Now, what happens is that typically it may be about 12 sessions or 15 sessions, depending upon the condition of the patient, which will span over 2 months. And my collaborator in Singapore General Hospital, Dr. Ng Isian, who was the head of rehabilitation medicine, so he was telling that often they come across a situation that at the end of 2 months rehabilitation therapy, they found that it was not very effective. One of the reasons is that they spend so much of effort on one particular part of the body, but at the end they realize that the recovery was not up to the expectation. So one of the limiting factor is that because the fMRI scan is not able to be done so frequently, right? Because it is expensive, there is a waiting time, there is a radiation hazard. So can we think about an alternative, economical, portable neuroimaging system using EEG as an alternative to fMRI? So that was the motivation for our work on EEG-based low-cost portable neuroimaging technique as an alternative to fMRI. Now, when I say alternative to fMRI, I should admit that this is certainly the quality is not comparable with fMRI because EEG has a poor spatial resolution. But what can be done? That is what we started looking into this. Now, the advantage of this is that we can do EEG scanning as many number of times. There is no limitation. It is an economical one. There is no waiting time. It can be done at home, portable. And more importantly, when the patient is doing the therapy, rehabilitation therapy, we can take the EEG scan, which is not possible with an fMRI or any other scanning techniques. So the connectivity, the functional connectivity can be analyzed using EEG-based neuroimaging. Now, let me show you this cortical activation map during the left-hand motor imagery of the left-hand stroke-affected patient. I'll show you the neuroimage that we have reconstructed with EEG. Okay, so you can see the resolution is fair enough, but certainly not comparable with fMRI. This is a humble start. A lot more work has to be done. But if this is done with a reasonable, of course, I will never claim it will be equal to fMRI, but this is a good compromise between economics, portability, training intensity, and more importantly, when the patient is doing the exercise, we can do that. Now, the second type of work that we are doing on enhancing cognitive abilities, attention and memory. So let me show you some of the games that we have done.
In this mode, there are 2 participants to play the game. The 2 players have worn Muse devices for EEG acquisition from which the attention scores are computed. They compete with each other to win the race by reaching the destination within a minimum time duration. Motivated to improve their attention levels to win the race.
So what you can see in this is that the green and the red bar graph indicates the real-time attention score of the respective players. And the higher the attention, the higher the speed of the car. And we did this experiment by cutting down this feedback. So this is called the neurofeedback or the visual feedback. So we did this experiment with feedback and without feedback. And as expected, it was clearly demonstrated that neurofeedback certainly helps to improve the attention score. So that's the gist of this game. Now, we also introduced some distractions during the game to measure how covert attention, which is an attention without fixating the gaze, affects the actual attention. And we did some studies. So these are some of the results. The first set of graphs, you can see overt trials, which means attention when the gaze is fixated onto the task, on the particular spot. So you can see that the attention score improves over different trials in both overt and covert trials. And this is the time taken for completing the game. And as expected, you can again see that from trial 1 to the last trial, there is a substantial reduction in the time taken. Of course, we also have quantified the continuous attention score using different signal processing metrics like band power ratio, sample entropy scores, etc. And this is the restoration time taken when the covert attention distraction is introduced. So we also developed a memory game. I know we are running short of time.
This works. In this game, EEG signals are acquired using Muse device. The player has to focus on a 3-element matrix for 1 minute. She has to memorize the locations and items for a fixed period of time and to refill them correctly for the successful completion of the game. Following this, a question mark will be displayed in one cell. At this time, the player needs to focus towards the screen by improving her attention level. The options for filling the cell will appear only when the attention level of the player is greater than the predetermined attention threshold. The attention level of the player is computed from EEG samples recorded using Muse device. The player selects the right option using right and left arrow keys on keyboard. In this way,
game,
the
what we
cells
have
are
done
to
is
be
we have integrated attention and memory. And in phase 1 of the game, the player has to use the right arrow or left arrow to select the choices on the right or left side respectively. And in phase 2 or session 2 of the game, we have asked the player to use his motor imagery, right hand versus left hand motor imagery, to choose the answer. And this is my last slide, in which we were looking into how can we exploit EEG error related potentials to do some corrective action. Now let me explain to you. So any errors that we commit during any task, there is an error related potential triggered. And even when we observe somebody else making an error, there is an error related potential triggered in our EEG signal. So can we use that error related potential to correct the errors? That is a question that we try to address. Just to give you a simple illustration, if you look at this rectangles here, you have the green square, which is the starting point of the cursor. And the cursor is programmed to move either towards the destination. The destination in this case is the red square, or the cursor is programmed to move away from the cursor randomly. So it can either move towards or away. Now at time t is equal to t plus 1, you can see that the cursor has moved one step closer to the target, which is defined as a correct movement. And when there is a correct movement, you can see there's a blue line. This is reflected in the EEG. And t is equal to t plus 2. What happens is the cursor has moved away from the target, which is an incorrect or erroneous movement. So the expectation is cursor should move towards the target. At the time t plus 2, an erroneous movement happened because the cursor has moved away from the target. And what you see is the red plot, which is actually called error-related negativity. You can see a big negative peak, which occurs at around 250 to 300 milliseconds here. And we can detect and decode that. So using that, The
experiment has 3 steps. Motor imagination, where subject imagines the hand movement towards the bee that appear either on the left or right side of the screen. Second, feedback, where the animation of the hand move towards the direction decoded by a trained motor imagination decoding model. Third, a corrective action, where the decoded MI actions are corrected using a trained ear.
So I think in the interest of time, I will skip the process. So basically what we have done is that the previous work, which different direction imagination decoding, whenever the patient makes a mistake, it's actually, we cannot say the patient make a mistake. Maybe the BCA system does the wrong classification, which is against the intention of the patient. This error correction loop using error potential is used to detect that error and correct the action. So that is the one. And again, we have used this for some kind of mild cognitive impairment. For example, if the fruit diagram is displayed here, and if the label is incorrect as a flower, that triggers an error potential. So this is these kind of experiments could be used for mild cognitive impairment assessment, and some person identification also done. And that's all. Thank you. And this is the acknowledgement. And thank you very much.
Thank you, Vinod, for the very comprehensive introduction and explanation of some of your very exciting BCI work. No worries if you have more to share. We have a discussion session later on. So without further ado, we are moving on to our next 2 speakers. The next speaker is Associate Professor Morteza Amjadi from University of Glasgow. Morteza is an Associate Professor of Biomedical Engineering at Glasgow Uni. His research team aims to design multifunctional soft machines utilizing novel mechanical designs, advanced materials, bio-inspired structures, and digital manufacturing processes. Now, such soft systems have many applications, ranging from wearable medical devices for healthcare monitoring to non-invasive surgical tools and soft robots for safe human-robot interaction. Today, he will present to us a topic on functional nanomaterial composites for soft sensing and actuation. Over to you, Morteza.
Hello, can you hear me well?
Yes.
Do you see my presentation?
Yes, we do.
Okay, great. So hello, good morning and good afternoon, everyone. And I'm glad to be in this symposium. So my name is Morteza, and I'm perhaps one of, the newest member of staff at the Biomedical Division of the James Watt School of Engineering at the University of Glasgow. So I'm going to present some of our research activities on functional nanomaterial composites for soft sensing and actuation. So the very first fundamental question is, so why do we need to make devices or machines from soft materials? In fact, as professor, we demonstrated some of the devices for rehabilitation purposes. So these devices that they already have well-established technologies. They are, especially like robots or systems that can be very accurate and they can be programmed easily. However, these devices are made of rigid components. So that means usually in their interaction with the soft biological materials, with the human body, it's usually poor, which can lead to motion artifacts and noises. On the other hand, so if we make devices out of soft systems, so because the material is soft, so that means we will have very high safety compared to the rigid components. And also because these devices are flexible, so that means they are comfortable to be attached to the skin or to be wear. And also, like, this is a developing technology, so that means we have challenges, we have opportunities in this area. So this is basically the motivation of our research. So we want to make these soft systems which are comfortable, which they can offer high safety. So if you really look into the rigid components or rigid devices, especially in rehabilitation, so usually the weakest scores in surveys they get is the conformability and also the basically ease of use. To make devices or robots out of soft materials, so we often work with polymers, with elastomers. However, one of the key challenges in most of the soft materials is that they have usually poor electrical, magnetic storage or other properties, which we are interested in. So that's why the current trend is to combine soft materials with micro nanomaterials in the form of functional composite materials. So examples of functional composite material-based devices include flexible displays, wearable biosensors, flexible solar cells, stretchable batteries, soft magnetic robots, etc. So in our lab, we focus on 4 main topics. So we develop soft sensors based on soft nanocomposites for healthcare applications. We work on soft actuators for soft robotics, and we explore skin adhesive materials and structure. And finally, we look into the ways how we can integrate these components, like soft sensors with soft actuators, soft robotic systems with soft sensors, and so on. So in the next slides, basically, I'm going to provide examples for each of these topics. So in the area of soft sensors, we have developed soft sensor solutions to monitor respiration, blood pressure, blood flow pressure, ECG, human body motions, muscle activities, gait, workout. So on the top figures, you see we have developed stretchable strain sensors, which are very flexible, and they can be placed onto the skin or onto the clothing directly. And in one of the examples you see on the right side, top right, so we can stick these sensors to the clothing and we can monitor the respiration. On the bottom left, so you see we developed flexible pressure sensors, and we have shown that we can use these sensors to monitor blood pressure on the wrist. And also we developed this flexible ECG sensors to, in real time, to detect ECG signals. So to go a little bit in more detail, so this is the example of our work on silver nanowire nanocomposite sensors. So basically here we have a very thin micron scale nanocomposite layer of silver nanowire embedded between two layers of PDMS, which is a kind of a flexible elastomer. And as you see on the figure, so these sensors are very flexible, they're very stretchy. On the right side, you see some electromechanical experiments we conducted. And if we define the gauge factor as the relative change of the electrical resistance of these sensors divided by the applied strain, then basically the gauge factor we achieved was in the range of 2 to 5. And as you see on the bottom figure, so these sensors, they can detect up to 70% of strain with a basically reversible response. So in another example, recently, so we worked with micro crack sensors to basically tune the sum of the sensing performance. For example, in the case of silver nanowire sensors, the sensitivity was low, so we were not able to detect very tiny movements. So here we basically work with engineering substrates. So we use 3D printer. We created this kind of wavy structure substrate, and then we coated this substrate with conductive materials, which in this case was carbon nanofiber PEDOT-PSS. And as you see on the ASM images on the top, so on the valley areas, we deposited more material, so we could get like materials with thick, basically, thickness. On the other hand, on the peak, we could achieve films with even nanometer scale thickness. So this variable thickness conductive films help us to control the crack generation on these conductive films upon stretching, as you see on the SEM images on the bottom left side. And as you see on the electromechanical measurements, we can then use this technique to tune sensitivity, to tune linearity and stretchability of these sensors. So on pressure sensors, so for example, in this example, we used a carbon nanotube polyimide nanocomposite microdome structure to develop high performance pressure sensors. And as you see on the top right figure, so when we apply pressure to this structure, because of the deformation of this nanocomposite, we get more current passing through this composite material. And as you see on the right bottom figure, so we can, with this sensor technology, we can detect extremely small to extremely large pressures. And the reason is we introduced these microstructures to improve the sensitivity of these pressure sensors for low pressure measurements. At the same time, we use this polyimide substrate, which is a tough, durable material, in order to measure very high pressures. So along with our experimental works, we also developed different modeling tools to understand the electromechanical properties of these sensors. So on the top is an example of our model of the percolation network of silver nanowire PDMS, basically nanocomposite sensors, where we assigned these nanowires, and then we looked into the repositioning and reorientation of these nanowires on the space when we stretch the nanocomposite sensors. On the bottom left, we used FEA tools to basically optimize the deformation of microstructure pressure sensors. And on the bottom right, so we developed this modeling tool to understand how geometrical engineering can affect the sensing performance of flexible strain sensors. So in the area of soft actuators, we worked a lot on paper-based substrate and nanocomposites, and we have shown that we can use paper-based composite materials as bending sensors, as electroresistive heaters, and high-performance soft actuators. So in this example, for example, we have used silver nanowire PEDAT-PSS coating on paper to make some conductive nanocomposites which are extremely robust even under folding cycles. And we have shown that we can use these kind of composite materials for electroresistive heating, for bending, sensing, and so on. And also combine this composite paper with basically polypropylene film. We have shown that we can create some soft actuators with very large and fast response to electrical stimulation. So one of the big challenges in this area is, okay, so we develop this soft sensors, these soft components, but the key challenge is how we are going to attach them, especially onto the skin. This work, we basically work with gecko-inspired structures, and we have shown that we can use this kind of composite microfibers to develop some adhesive patches which can be strongly sticky on the skin. And we also explored the breathability of these patches, and also how the long-term use of these patches can basically stimulate the irritation of the skin. I think one of the key areas we are very interested in is the integration. So we develop these soft sensors, we develop these soft actuators, soft pressure sensors. Now the question is how actually we can use them in practice, in practical applications, because for practical applications, we need to integrate these sensors, these technologies with the data acquisition systems, with control, with other components, with batteries, with energy storage, and so on. So here are some of the examples. So the first example on the left side is a telerobotic. So we use these sensors to create a smart glove system, and we developed this miniature chip to basically to collect and to calibrate the data we get from the sensors, and for wireless transfer to a computer. Second example is, so we have used the sensors to control the soft endoscopic robot. So we use this sensor information as an input to basically control the robot. In the pressure sensor example, so we have reported or we have created a flexible pressure sensor array, and we have shown that we can use such a sensor array to basically monitor the pressure distribution in the soul. And we were able to basically distinguish signals between walking, jumping, and running, and so on. So in soft robotics, for example, we worked with the self-sensing soft actuators. So in this example, I'm not going to go through the details, but we developed a hybrid conductive ink, and we have shown that we can use that ink in soft actuators for sensing purposes. On the right side, we, for example, integrated our soft strain sensors with soft grip robots, and we have shown that these sensors, these soft sensors, can provide useful information while the robot is doing picking and touching external objects. And another example of the integrated soft system. So here we use soft sensors, we integrated it with the Wi-Fi, and we used the internet to store the data in a cloud-based system. And basically here we put a sensor on a tomato, and we monitor the growth of the tomato over 17 days. And as you see here, for two tomatoes, one with the steady water supply and one with the intermittent water supply, so we clearly see the signal from the sensor. So we can basically monitor the progression or the regression of the growth of these tomatoes in real time. So so these are all examples like how we can use soft nanocomposite materials to develop sensors and actuators for soft robotic and healthcare applications. Thank you so much.
Thank you, Morteza, for the very fascinating work on soft robotics and all the possibilities. My mind is now buzzing with a lot of possible collaborations.
Thank you so much.
Last but not least, we have our free speaker from SIT to round up the session before we break up into a 20-minute break and then a discussion session. So let me introduce Associate Professor Desmond Chong from SIT. Desmond is currently an Associate Professor with the Engineering Cluster at SIT. His research interests are in the area of orthopedic and musculoskeletal biomechanics, finite element analysis and experimentation, medical devices design, joint implants and rehabilitation, gait and motion, human motion analysis. His presentation topic here today is on sensors for biomechanics and healthcare applications. Over to you, Desmond.
All right, thanks, Pei-Ling. Can you hear me?
Yes,
everyone?
very well.
Okay, good. Thanks, Pei-Ling, for the in-kind introduction. And of course, first thanks also to the organizers for actually inviting me to give this talk. So I think early on, we had a speaker talking about, all the soft sensors. I guess I kind of did not really prepare my talk more towards from the research perspective. It's really more like a general kind of sharing, but I see what I can do. All right, so my topic is actually on sensors for biomechanics and healthcare applications. So I'm a mechanical engineer turned biomedical engineer. All right, so yeah, I mean, we definitely hear a lot, in our previous speakers in this particular session, and I guess also speakers from a different, from the other track. I think we are closer and closer, building a bionic body, with Human 2.0, with all the various kind of sensors, implants, and processes actually put in place. With all the AI, machine learning, even soft sensors. I think we are really moving towards Iron Man 4.0, okay, and even probably beyond. All right, so this is the outline of my presentation. Actually, I'm going to do a quick introduction and sensors for healthcare applications. Then I'll touch briefly on wearable sensors for healthcare. After sitting through the session for definitely for 1.5 hours or so, I really have to make the declaration that, or the acknowledgement that I'm no expert in wearable sensors. They're actually much more experts who are actually sitting in this audience. All right. So of course, then I'll move on to talk more about our sensors for biomechanics studies and probably just give a quick summary. All right. So well, I mean, in terms of the sensors, we're talking about traditional sensors. We talk about airflows, pressure, oxygen, temperature, magnetic thermistor, humidity, position sensors, even force sensors. All these sensors has been used actually very traditionally in medical devices for all various kind of applications, whether you monitoring of the vital signs or actually more for biomechanical analysis, right? So of course, we have the strain gauges and also the LVDT and the DVRT. They are actually more measuring of the displacement, and also strain gauges is really more measuring on the deformation of the body or musculoskeletal of interest. So I mean, let's say we move into the wearable sensors for healthcare. I believe there are 4 major types of wearable sensors, that actually touch on different kind of technology. So of course, it can be classified into chemical, electromechanical, optical, and electrical sensors. So the first is, the chemical sensors is really measuring of the concentration levels of chemicals in sweat, blood, saliva, and other bodily fluids, right? So some examples include the glucose monitors for diabetes, and also the lactate level measurements, as well as moving into using the sweat sensors to measure the stress hormones, right? So I think this is the Freestyle Libra, the diabetics care. This particular device is actually worn on the back of an upper arm. It's really used to measure the glucose level, right, in the interstitial fluid between cells. So I mean, just quickly Google, and of course, with this, Lila Moss. So if you all know, she's actually the daughter for Kate Moss, who is the supermodel from UK. Yeah, the thing is, you can see that even though she's actually in a campaign in her own modeling work, she actually has been wearing this blood insulin monitor, without any kind of worry. So she's actually openly acknowledged that she's a type 1 diabetic subject. All right. So of course, you move on to electromechanical sensors. We look about it's really using electrical measurements to track the mechanical movements. Early on we talked about human movements, we talk about gait analysis. All those things are relying on the accelerometers, the inertial measurement units, the electroganometer, and even the position sensors. right? So the third type is, of course, the optical sensors that we are probably used to. We know that it actually uses light to detect various biological signals like heart rate, oxygen saturation, and blood pressure. So of course, last but not least is the electrical sensors that really uses electrical signals to measure the heart rate, the brain activity, or the muscle activity. I guess early on, Professor Vinod has also mentioned about his study in using EEG, right? Yeah. Okay, so looking into some of this literature review, so I come across this particular work by Majanda, et al. So already in 2017, they looked into some of these wearable sensors for remote health monitoring. So of course, they first started looking into some of those they are commercially available products, right? It's already there out in the market, to measure various types of like heart rate, even the sleep stages, the number of steps, the distance traveled, and all those things, and kind of like more of the vital signs. And I was just surprised that, of course, in terms of the battery, you can see that all these kind of wearable sensors, they can actually last like between like 5 to 7 days. So interestingly, I'm not sure why they actually missing out, the Samsung Galaxy Watch and the Apple Watch. All right. So of course, looking into the sensors itself definitely is the essence. But I guess if you want to actually make it a total health monitoring system, so I guess you can actually put as many sensors on the body, whether you're going to measure cardiovascular, you're going to measure, kinematics and kinetics, right? You're going to measure the blood oxygen level, the pulse, and the blood pressure. You need all these signals to actually go to this body sensor network. Eventually, you might want to actually go to a home gateway, because sometimes the data probably storage is limited in this particular small network node. So you need to actually kind of transfer the data to the home network. But of course, nowadays people are talking about tele-rehabilitation, right? So telemedicine, sorry. So you'll be actually transmitting all this data through the internet, and that's where the healthcare providers, in hospitals and the clinics are able to view all the various important signatures and as in signs that you're capturing from the body. Not only that, I guess in terms of you're going to wear motion sensors on the arm, on the leg, definitely we are there to actually kind of measure what are the activities, right? So when you're actually putting a wearable sensors, you're not just like bounded in a gate lag where you're actually limited to certain activities. So you're wearing the wearable sensors, you can definitely look into walking, jogging, running, ascending and descending slopes and stairs. Not only bounded in the lab environment, you can actually do all the activities outdoor as well. Okay, so of course, recently, there are also people looking about sensors. I guess wound healing or wound monitoring is something that I guess they actually gained a lot of research interest recently, right? So depending on how are you going to actually develop a sensor, for wound monitoring, for recovery or wound healing. So they're really looking into the different types of wound biomarkers, right? Whether you're talking about using biomolecules, you're using proteins, or using some form of pH level, or you're really looking more towards the physical, like measuring of the temperature, measuring of the pressure that you can actually measure. But eventually, you need to kind of like really analyze them, and eventually, provide some form of like data acquisition or some kind of display of the results, such that clinicians and patients themselves are able to view and actually analyze or even appreciate themselves. All right, so quickly, I just want to actually move into how do we use, like sensors for biomechanics studies. So this is just a quick kind of like overview on like what are the different branches of biomechanics, whether you can look into the very bone and tissue mechanics, look into musculoskeletal. You can also apply biomechanics into sports, orthopedics. You do general gauge human motion analysis. And of course, you can use that for development of rehab and assistive devices as well. Of course, you look into neuromuscular biomechanics. All right. So I guess very common, when you talk about biomechanics, we talk about gait analysis. We actually utilize the motion capture analysis lab, right? So this is very common that you have all the infrared cameras. Those are optical sensors in nature, right? That's where they capture the kinematics, the joint angles, and also the temperature of the individual walking. And you have the force plates. The force plates are a form of like electromechanical, right, sensors that actually really measures the ground reaction force, how the ground reaction forces are actually returning through to the body, right, for musculoskeletal analysis. and you also can mount the EMG. EMG will be more of the electrical sensors. It's ready to kind of like capture the muscle activities, right? So I mean, not only that, there are also those kind of like insole systems, right? That like for example, from the F-scan systems, if you really want to measure the foot plantar pressure of individuals, right, when they're actually walking. So especially they are actually getting a lot of interest in terms of diabetic patients, right? So for diabetic patients, when they actually have developed neuropathy, that's where they actually lost the sensory of touch, sensory of touch, so that in a way they are not able to actually feel, are they applying any high pressure at a particular point at the plantar side of the foot. So this kind of like insole sensors will be very helpful for them to actually monitor, in terms of their gait pattern and also the plantar foot pressures. So these are some of the kind of like sensors that are actually available, for research purpose. So how people actually use all these sensors for biomechanical studies. So of course, one of the example, of course, our first speaker, Prof. He mentioned about stroke patients, stroke rehabilitation, right? So people have been using gait analysis, motion capture to actually study, what is the gait pattern between a normal subject versus stroke subjects. Why? It's really to see what's the difference between a normal gait and an abnormal gait from a post-stroke patient. So from there, definitely interventions or rehabilitation regimes can be kind of more targeted for individuals, right? So I think definitely we can see that this is actually an example of an uncorrected post-stroke patient. So typically when we start to actually walk, you can see that when we swing our legs, it's actually mainly in the sagittal plane, right? But you can see that for post-stroke patient, he may have to actually swing the foot, upwards, right, about the frontal plane as well. So that is actually not a very kind of like a normal gait, and probably more muscles have to be recruited to actually perform a single step. And I think you can see that there's a foot drop over here as well. And this is always the kind of like gait pattern that biomechanics engineers and also doctors would like to actually look into. So the next, another study, I've actually wanted to share is, of course, doctors and biomedical engineers, they actually recruited subjects to go for gait analysis. So this is the study from a group from Korea, right? So actually they retrospectively reviewed the medical records of 102 patients, right, with hemiplegic stroke who actually underwent gait analysis. So what they actually trying to look into is, of course, correlations between various temporal spatial parameters. All right, so of course they have it with other scores as well. So what they have actually kind of like really found is that, the gait speed and height and the lower limb stance space time were the only temporal and spatial parameters that actually shows a statistical correlation with motor and balance function. So with that, in a way, they kind of actually bring them to kind of prescribe some rehabilitative treatments. So with that, they says that the rehabilitative treatments focusing on increasing gait speed and shortening of the stance space time of the unaffected side may actually improve the ambulatory and balance functions in these post-stroke patients. All right. So of course, again, sensors are also used for another applications, where this is a group of researchers from Taiwan. So what they are trying to look at is the effect of the 3D printing, right, of this hinge ankle foot orthosis for equinovarus control in stroke patients. So this is actually how an equinovarus foot actually looks like. So because if you have this equinovarus foot, what you can see is that when they start to walk, they actually apply a lot of plantar pressure or overload at the lateral sole, right? So can there be some correction? Yes, there might be some corrections. You might want to ask the patients to actually alter their gait. But let's say because of the nature, they might not be able to, you need to actually prescribe some form of orthosis for them. So this group of researchers in Taiwan, they actually come up with a 3D printed foot orthosis, right? So it's actually very customized because they are able to scan the individual profile or the contour of the foot of the individual. Then they actually 3D print this very customized orthosis for the subjects or for the patient. But the question is that, how do you know this 3D printed orthosis is able to help to relieve the lateral plantar pressure? All right. So what they have done is that they actually rely on the insole systems. Of course, what they're using is they are using the PIDA X insole system. And with that, they inserted this PIDA insole systems together with the 3D printed orthosis that we have actually built. So what they have actually found out is walking with their 3D printed foot orthosis, right, in a way reveals significant increase in the medial midfoot peak pressure compared to a barefoot walking. So you can see now is that originally they are seeing much more higher pressure at the lateral side, but after wearing this 3D printed in orthosis, right, you can see that actually the pressure point actually kind of move from the lateral to the medial. So that says that the lateral side is definitely kind of like offloaded. So with that, they are able to show that, you know, wearing their 3D printed ankle foot orthosis increase the plantar pressure in the midfoot and actually make the entire kind of like contact area more symmetric. And so in a way, they are using sensors technology to prove that their orthosis actually helps in actually altering the plantar pressure of the individuals, right? So in terms of the research, so I also collaborated with a group of clinicians and biomedical engineers with Prince of Soka University, Thailand. So again, when we wanted to kind of compare post-stroke patients with the healthy subjects, first you must actually recruit healthy subjects, you know, to gather the normal data. So the group from Thailand, they wanted to collect the data which is actually more towards their own demographics. So they actually look into the difference in the knee muscles activities during walking between healthy male and female elderly. Right. So with that, you know, of course, they recruited some of the patients. Because this is the prelim studies, you know, they have 5 female and 5 males, and actually they mounted the EMG sensors, you know, at the biceps and the quadriceps and the biceps and the quadriceps. All right. So what they have done is that actually they found no difference between the kind of like knee muscles activities between the male and female. So with that, they are able to actually kind of like group this male and female as a group of healthy subjects. So with that, they move on to recruit the stroke patients. So in terms of the stroke patients, of course, they actually mounted more EMG sensors at more muscles, you know, at the lower limb itself. And because these studies is still in progress, so I will not be able to share, you know, all the results, but I'm just going to share some of these prelim results and also limited results just to show that what is the significance between stroke patients and actually healthy subjects, right? So what they've done is that they tried to actually look into a gait analysis. You know, in terms of gait, it can be divided into the first double support, when they go into the single support, then go into the second double support, followed by the swing phase. So what they have done is that they try to look into what is the percentage of, you know, of these various phases for the healthy subjects versus the non-paralytic side of the stroke patients versus the paralytic side of the leg. So you can see that definitely in a way they in terms of the healthy subjects, they're actually taking shorter time, right, in terms of the double support, the single support, and also the second double support. All right, and it's only at the swing phase, and that's where the healthy subjects, they are actually, you know, taking a more time in the swing phase itself. So looking into the muscles, so I'm just going to show you the, you know, the gluteus medius muscles. So very clearly we can see that in terms of healthy subjects, the muscle recruitment activity, you know, for the healthy subjects are actually definitely more powerful, right, in the first double support phase. And we can see that even for the non-paralytic, in a way, the muscle activities is already lower compared to the healthy subjects. So I guess with all this kind of analysis, we will be able to show that what are the muscles that are actually kind of significantly weaker in the stroke patients. And so in terms of the rehab regimes, I guess that's where the rehab doctors and also the physiotherapists would be able to kind of like cater the rehab kind of protocol or the rehab regime more specifically targeted to this group of post-stroke patients. So moving from the gait analysis, from rehabilitation, just wanted to move quickly in the space of orthopedics, right? So in terms of orthopedics, this is a work that I actually work with a group of orthopedic surgeons with the University of Malaya, right? So what they are looking at is, you know, this proximal fibular osteotomy, right? So I can see that this is a knee joint. So the knee joint, you can see that actually in the medial compartment, there's actually a collapse. There are actually no gaps, right? So because of this collapse, again, that's where the patients are feeling some pains I think this is due to osteoarthritis, right? So you know that for osteoarthritis, if it's actually at the end stage, you know, in the worst case, that the patient have to go for a total knee replacement, which is quite a major surgery. So especially for elderly, they wanted to actually delay the chances of going to total knee replacement. So the clinicians are saying that what if we actually remove this proximal fibula? Would it help in actually kind of offloading or transfer of the load from the medial compartment to the lateral compartment? So interestingly, it actually does help. We can see that the gap did open up. So the patient will not feel much pain at the medial compartment. So the questions from the clinicians will be, by doing that, right, how are you going to alter the strains, you know, the stresses that are actually kind of like being accumulated at the proximal tibia? So what we've done is that we actually embarked on a cadaveric study, right? So from the cadavers, we then mount strain gauges and strain rosettes. So strain gauges, strain rosettes is a kind of sensors that actually measure the strain to show how much force or how much load or how much deformation that the proximal tibia is going to deform, right? So from there, we use the mechanical testers to prescribe a physiological loading condition, right? So of course, with that, I don't want to go through all the various details. So in the way, definitely, we actually show some results to show that there's actually some significant increase in the lateral tibia strain adjacent to the proximal tibial fibula joint, right? So some of the conclusions can be says that, you know, the increase in the lateral and the proximal tibial strains, right, actually raises some concern of long-term failure for the patients who actually receive this PFO. So we are able to give some indications for the orthopedic surgeons. You know, when you do this kind of operations, what are the kind of like possible impact that you'll be giving, you know, passing over to the patients. And this is just another example. This is another study to look into patellar transverse fracture, right? So in terms of patellar transverse fractures, orthopedic surgeons have different techniques of actually repairing this fracture, right? So this group of patients, this group of doctors, they are from Ng Teng Fong General Hospital and also from National University Hospital. So the question is that, okay, we are going to use the conventional tension band wiring versus the new tightrope fixation. So depending on the different kind of techniques, are we able to kind of like, you know, analyze from a biomechanical point of view, is there any kind of like compromise in terms of the new technique that the surgeons are implementing? So what we are doing here is that we try to measure what is the gap of the fracture that has been repaired. So in terms of the measurements, so what we did was we used the DVRT, which is actually the displacement sensor, to actually measure the gap. Right, so what it was done is that after patching up the gap, and we actually use cadavers as well, we actually do a cyclic loading of flexion extension of the knee joint. So with that, we try to measure, you know, the gap at 50th cycle, 100, 200, and the 500 cycle. So from there, we try to compare the gaps between the traditional, you know, tension wire versus the tightrope. So at the end of 500 cycles, yeah, although in terms of the numbers, the new method, it was like having a gap of 0.355, right? But in a way, we shows that it was actually non-significantly different. So it gives the surgeons a confidence that, okay, when you use the new technique, at least from biomechanically, you know, the new method is actually not worse off compared to the traditional method. All right. So just to move on, yeah. So again, these are some of the other studies that we try to measure when you actually place the knee implant onto the knee, on the proximal tibia. Now, how much the kind of like knee implants are actually moving when it's subjected to a tibial load, you see. So the issue is that the lower the bone prosthesis relative movements between the tray and the bone, the chances is that the fixation of the implant is actually better. So in the long run, the implant is not going to fail by long-term loosening. So again, we try to measure this kind of like displacement at the lab level. And again, we are using the displacement sensor, which is the LVDT. All right. So I think moving back, I just want to show other examples. So the thing is that you can see that all these implants, probably we were seeing that it's actually all measuring at the cadaveric level. Are we able to measure the actual contact forces that are actually in vivo, you know, in the human body? So definitely, you know, the group of researchers in Germany, they have already kind of like come up with what we call the instrumented implants. So can you imagine these instrumented implants? They are ray implants, they have 4 sensors, they have strain gauges, incorporated into these implants. And these implants are then, kind of fitted into actual patients. So when the patients are actually wearing these instrumented implants, we are able to measure the actual forces that are actually experiencing at the particular joint of interest. So for this case, they are looking into the knee joint. They also have the instrumented implants where for shoulder joint purpose, they are also able to actually measure the joint forces at the shoulder joint, in vivo, right? So what do we do with all these forces? The thing is that what we do is we try to actually use these forces, import into our finite element analysis, kind of like computational study, right? So what we've done is that we actually started off from the CT images. We tried to build the bones with 3D reconstruction, and we try to do a virtual implant placement. After the implant placement, we need to actually prescribe the physiological loading conditions. So nothing beats if you can actually measure the actual joint forces that are actually measured from patients. We will then be able to put into our computational model to actually make a better and a more accurate predictions, and it'll be helpful for us to design new implants. All right, as I guess in view of time, I'm just going to stop here. So this is hopefully give you an overview of like what are the sensors that are available and how these various sensors can be used in the biomechanics and orthopedics applications. All right, now thanks. Back to you, Pei Ling.
Thank you very much, Desmond. No worries, we will have a discussion forum later, so we can have you back to discuss more ideas or what you want to share later on.
Thank you.
No worries. So for now, I think everybody will need a break, a short break of 20 minutes. So we haven't ended the session, just to be clear. So after 20 minutes of break, we return back here for a discussion on robotics and sensors. So the time for coming back for our Singapore friends will be 5:50, and for Glasgow side, it will be 10:50 a.m. So see everyone shortly.
Thanks, Pei Ling. Thanks a lot.
So see you.